class. So we've covered appearance, we've covered chemical properties, corrosion resistance, electrical properties, electrical conductivity, and we're going to finish up with the last one, which is thermal conductivity. Now this is by no means a Webster's dictionary definition for thermal conductivity, but it's kind of my easy definition. It's the ease at which heat can move through and leave a material or a metal, right? And like Ron talked about how current can go at different rates through a material, and that's what gives its electrical conductivity. Metals all have thermal conductivity. All metals will allow heat to pass through them, but all metals do not let the heat dissipate out of them at the same rate of speed. So we're going to use an example. I'm going to have a couple different coupons, and I'm going to put a weld on them. Weld on that one, and a weld on that one, right? So this is my carbon steel, this is my stainless steel, and this is my aluminum, right? And I weld them all at the same time. They're all going to get really hot because I got to get them hot enough to get the weld to fuse together. Some are going to get hotter than others because carbon steel, it's got to melt at like 2,300 degrees. Don't quote me on it, it's not an exact number. Stainless steel, we're going to melt that dude at about 2,100 degrees, and this one we're going to melt at about 1,100 degrees Fahrenheit. Now those are not actual specific numbers, but they're pretty close. I weld them all at the same time. I stop the welding, I walk away. 5 minutes later I come back. What's the heat absorbed in these pieces? Are they still hot? Are they really hot? Or are they extremely hot? And I know that's a generic measurement, but as a welder, that's how I'm going to do it today. The carbon steel you're going to find has cooled rapidly, right? It's probably still going to be warm, maybe warm enough to where you don't want to touch it, but it's not blistering hot, right? The stainless steel, probably going to be hotter. It's probably still going to be up around the 800-900,000 degrees Fahrenheit, where that one's at 200-300 degrees. The aluminum is still going to be raging hot, right? I mean, you touch it for a split second, it's going to burn you, right? And this has everything to do with thermal conductivity. They all let heat go through them, but they dissipate heat in a different time scale, right? And when we talk about that, and I know that's a really generic way to put it, when we weld these things, heat does weird things to product, right? Because of expansion and contraction, and when a part heats up, it expands, and when it cools down, it contracts. There's different expansion and contraction rates happening in the weld and outside of the weld in the base material. And what happens is, when you weld a piece and it cools and it twists and it contracts, it distorts. So a lot of times when you deal with stainless steel and aluminum, you have a lot of issues with warpage and distortion, and it has to do with its thermal conductivity. It stays hotter longer, therefore you get different expansion contraction rates in and around the weldment in the part, and that thing starts out like a flat plate, and by the time you're done welding, it's rolled up into a taco. That has everything to do with thermal conductivity. So when you start talking about we're welders, what's the weldability of it? It's different, right? If it was just carbon steel, just weld it, man. It's not a big deal. If it's stainless steel, you have to be really careful with your heat input, you have to be really careful with your travel speed, and you have to be really careful with where you put your welds, right? Because if you put all your heat centralized in one part, it's going to warp and roll up into a taco like we talked about. You started off with a square frame, and now you have 2 inches out of square frame because you localized all your heat into one area, and because of thermal conductivity, it warped the heck out of stainless steel, right? Aluminum does the same thing, but not only will it warp and distort, it actually apply a lot of stress to your welds, and before it ever cools back down to room temperature, a lot of times your welds will fail and crack. And a lot of times they'll say, well, aluminum has a hot short property. It's a big term for it stays way hotter, way longer, has a lot of different weird things happening with expansion and contraction rates. Therefore, it puts a lot of stress on the weld, and if you're not careful, your welds will crack prematurely before it ever gets back to room temperature. So, what are some things we do as welders? Carbon steel, don't have a lot of problems with thermal conductivity. Stainless steel. Well, I don't want to get real deep with this class because you guys don't have a lot of welding experience your first term, but sometimes it boils down to the welding process you're using, right? Maybe shielded metal arc welding is not the most desirable welding process for stainless steel. Can you weld it with stick? Yeah. But if it's thin metal, maybe stick isn't the right process. Maybe you should go to TIG or a MIG application. Sometimes they will switch the welding process because of the warpage and distortion issues caused by thermal conductivity, right? Maybe they do back welding where they'll do a weld, and traditionally, if I had a T-joint, and I'll draw one up here really quick for you guys. There's my T-joint. Traditionally, with what you guys have ran, you'll start here and you'll weld and you'll finish there, no matter how long it is. It can be 10 foot long. In stainless steel and aluminum, sometimes they will back weld, where they'll do a weld here, from here to there, and then they'll come back 2 inches and they'll weld here, from here to there, and then they'll come back here and they'll weld from here to here. And that's very non-traditional. That's called back welding, and back welding controls heating, expansion, contraction rates in and around the weld and the part. And it controls warpage and distortion. A lot of times they do that on thinner stainless steels and aluminums to control expansion, contraction, warpage, and distortion issues caused by thermal conductivity. Then, what they may do is they may use a part that sucks and absorbs heat really well, right? So if I say, I want to weld this T-joint and I have to do it a very specific way, then I will set this T-joint on maybe a piece of brass. Some people use copper, and if you want to be just cheap and it'll work, aluminum. All of those suck up heat really well. They're like a magnet to heat. So I'll take my part and I'll set it what we call a chill plate, and all the heat being put into this part will be robbed by the chill plate that it's sitting on. So if I take my T-joint and I set it on a piece of brass, as I weld it, the brass is going to suck up all that heat out of my part, and it's going to control warpage and distortion issues. So there's a lot of different ways, from changing my welding process to changing my welding progression to using chill plates to control heating, expansion and contraction, distortion and warpage issues caused by thermal conductivity. Hopefully you guys will find this module useful. We could have went way deep into this, and we could have went way deep into any of these modules in this metallurgy class. But we have to be realistic about who we are and what we're trying to learn. We're welders trying to understand a little bit about metallurgy. If you want to be a material science engineer, then you most definitely need to go through a material science class and program, which is going to be a way longer duration of time. We got you for 30 hours this summer. 30 hours doesn't scratch the surface of metallurgy and the reality of things. So it seems like we're just touching on things, but as welders, all we need to know is a basic understanding. And if you want to be a welding engineer or a metallurgist or a material science engineer, then go after it, right? So hopefully you guys have found this useful this week. We'll see you next week.